we can deal with it. But I did start recording, so everybody's aware of that. Ask everybody to please mute yourself if you're not speaking. Type any questions into the chat box in the Teams meeting, and we'll address those towards the end. And then comments or questions you can send to our email address here. Okay, so that'll take us into our topic, pay now or pay later, using a risk-informed mindset for the site investigation decisions. We'll send a PDH link where you can download it after this meeting. I'm going to flip back to our survey here and go into the next question and ask you guys to fill in your responses here. Essentially, what is the term geotechnical subsurface investigation? For us, is mostly structural engineers. What does that mean to you? You can put in a couple options. We'd just be curious to see what everybody, what that brings to mind. Early in the project, late in the project. Bring one more time. And we'll see. All right, so it's good to see that somebody wrote borings, plural, not boring. Field recon, soil properties. Curious to know if anybody has any feelings on the idea of the cost or the expense, which is really going to be what Georgette and Vanessa go through us today. Is what happens if you don't put in the right efforts at the right time throughout the project cycle. Valuable. Okay, I think Georgette and Vanessa put that one in there. Thank you guys. All right. So with that, I'm going to, it's all very technical answers, but borings is the highest one. So with that, we'll go back to the presentation here and introduce our speakers, and then let them take it away. So today we have Georgette Halepas and Vanessa Bateman, both from the U.S. Army Corps of Engineers. Georgette and Vanessa, I'll ask you guys, instead of me just reading kind of the LinkedIn profile here, if you guys want to go ahead and unmute, introduce yourselves, and then when you're ready, Georgette, please go ahead and take the screen and walk us through.
Okay, so I'll introduce myself first, if that's okay. First, can you hear me, and can you see my shared screen?
We can hear you, and not your screen yet.
Okay, well, I'll work on that while I introduce myself. So my name is Georgette Halepas. I work for the U.S. Army Corps of Engineers. I'm currently working in headquarters, acting as a geotech, geology, and materials community practice lead. I've been with the Corps for about almost 15 years, doing all variety of geotechnical work. Majority of my work has been on dams and levees, and you'll see that in some of the examples. But I'm really happy to be here today to talk to you all about risk-informed decision-making and the subsurface. Vanessa?
Good afternoon. My name is Vanessa Bateman. I am actually currently the Chief of Civil Works Engineering at the U.S. Army Corps of Engineers, and so the Principal Geotechnical Engineer was actually my last job, although, that's fairly recent change, so good on you, James.
Congratulations.
I appreciate that. So I started my career as a geologist one at the Department of Transportation, running behind a drill rig. I've gotten the chance to do a wide variety of work within geotechnical engineering, both at a DOT and for the last however long now with the Army Corps of Engineers. And so I've gotten to do a lot of different kinds of projects, and this topic of subsurface investigation and how to do it better. What are the risks to your projects is something very near and dear to my heart. As I started out with muddy boots and muddy hands, and I still enjoy getting out behind a rig anytime I actually can. But there's a lot that we can bring to an investigation, and so that's one of the ways I want to talk about today is how we do this better. How do we work with you better, and how do we do better with our own part of the profession to be able to deliver better projects?
Excellent, thank you, Vanessa. All right, so Georgette, if you want to go ahead and share your screen, I'll stop sharing mine, and that'll take us to your slides.
Okay, thanks. Yeah, I think you might have to stop sharing for mine to work.
You're not. Are you still seeing my screen or no?
Yeah, your screen is up.
No, I don't see yours now.
Oh, maybe it's just me. Okay, I'm hitting open share tray. It's blinking on me. Vanessa, can you try from your screen?
Certainly. I'll go ahead and get started.
Okay, thanks, Vanessa. I'm sorry about that. It just keeps bouncing back to me.
Not a problem. All right, well, maybe. Oh, good Lord. Okay.
Is it freezing on you too?
Just for a moment, but it's taking just a second, so it'll be okay. You're going to see a blank screen here for just a moment.
Yeah, we can see your desktop now.
Great. Perfect. Let me make sure that this shows up on the correct screen. Here we go. All right, everybody ready?
That's good. Thank you.
All right, thanks very much. I really appreciate the invitation today. And as I said, this is a subject near and dear to my heart and certainly near and dear to Georgette's as well. Okay, so risk is one of those squishy words. People use it to mean a lot of different things. We all have different conceptions of what risks we can tolerate. We have different conceptions sometimes of what risks are involved in things. And so when we're starting to talk about risk, we need to be thinking about, what do we mean by that? What do we mean by that for our organization? What do we mean by that personally? What do we mean by that for our project? Because certain risks are going to be available in other parts of life that may not necessarily be realized on your project. And not every project is going to have the same level of risk, right? So if you're doing a poll for a stoplight in layer cake geology and this area is well explored and everybody really pretty much knows what it is, the risk in the subsurface for that project will be entirely different from something that is structurally complex, from something in karst terrain. So there's a lot of things that we have to think about here, and we need to be thinking about it in a much more structured manner. And communication is one of the biggest things here because we need to make sure we're all using the same words and that those words mean what we think it means. Risk is present throughout the project life. So we are, looks like it's hesitating on me here for a second. All right. There we go. It's in every phase of our project. We have risks that can be realized in planning, in engineering and design. We have risks that can show up during construction, and we have risks that can show up during long-term operation. And so when you're working on a project and when you want to take a risk-informed mindset, you need to fit your decisions to the detail and complexity that you're going to need at the time. I may need a different level of information in an early planning study than I'm going to need in engineering and design. I may need a different amount of information during long-term operation. And so part of using a risk-informed mindset with subsurface investigations and the geotech in general is to scale the work based on the detail that you actually need. All right, now, what is one of the biggest uncertainties we can deal with out there, right? It's the subsurface. If you don't know what to expect when you're laying out a site investigation, don't be surprised when somebody misses it. One of the biggest mistakes as an industry that we make, and I saw this many a time when I was, particularly in my early career, someone would say, I want this many borings. We're going to put up this square building, go drill one hole on each corner, and then write me the geotech report, and I'm going on from there. I'm going to build a bridge. And I just, we can't really afford all the time it's going to take you guys to get that drill rig out there. So just do one boring per pier. Okay, well, that can work in the right circumstances, and I had many a successful bridge project with just a few borings. And I had many a not so successful bridge projects when we came into the situation and we said, oh, you know what, we're not going to do what we need to do to actually manage the subsurface intelligence. So the information's not always easy to find, but don't worry. Your geotechnical engineer, your geologist can help you, because part of their job is to understand the environment that you want to build your structures in. And that knowledge is absolutely crucial for planning a good investigation. All right, so, and where are you in your project? How much uncertainty can your project take in what phase? Now, if we're doing a little bit of a desk study and we're just thinking about whether or not we actually want to build this thing, we don't need the same level of detail that we're going to need during design, and we don't necessarily need, definitely don't, in the early stages, we don't need the information that we may need during construction. And it can be asymptotic, right? We get a lot of information to get started. We walk out there and get a look at things, and then we plan out our main investigation. And then sometimes you have to come back and get supplementary investigation. That's the part that often drives project development teams crazy, is when you've gotten all this information and you realize, wait a minute, there's a risk here. There's uncertainty here that we haven't defined. And we didn't plan for it in the project schedule. And now you've got somebody coming in saying, about that, we need to go do this many more borings and some geophysics. And your project manager at this point, head's exploding and saying, well, why didn't you know that before? Well, in some cases, we couldn't have known that. So you've got to think about where you are in the phase of the project and how much uncertainty you could tolerate. Because it's okay to make a decision that we can tolerate a certain amount of uncertainty if we can bound what those consequences are, talk about what that risk is, and sometimes the right answer is yes to accept it. Many times, however, we need to be very careful about understanding that you can accept a risk that is a little bit more than you can chew. So you need to be careful about that. Site characterization is something that builds over time. Understanding of the ground conditions is necessary for on-budget and on-time engineering. Models are continually refined over time as understanding improves. There's a lot going on down there in the subsurface, and we need to make sure our models actually reflect the reality of what we're dealing with. And then risk is reassessed as additional information is acquired and understanding changes. And that's, I think, part of the frustrating part for some people is, you expect just one answer. And that's great. We love to only have one answer. But the problem is, if I only give you one answer in the planning phase, and when I find new information in the engineering and design phase, and I don't take that into account and make adjustments, then my site characterization that provides you the information you need to design these foundations can go wildly wrong. We want to know that we want to know that features like this are going to exist before we have to deal with them during construction, because we need to plan them, right? The most expensive time to make a change in the design is during construction. You want to know that this is there. You want to know what you're going to do to deal with it. You want to make sure that it's in the contract, and you're not in the middle of construction arguing with the contractor about who should have known what when, and having to make all of those kinds of changes. This is a picture on your left is from one of my projects. This is not what you want to find underneath your bridge spread footing. So this was actually a contract job. It was one hole per bridge pier. The rock was absolutely gorgeous. No flaws in it whatsoever. But what are you looking at over here on the left? Right, large karst feature, right underneath one of the substructures. We had to redesign the footing in the field, right then. Okay, so one hole per pier, that may be appropriate in the right circumstances, but it is never what you should assume for every project, right? You need to be talking to your geotechs, talking to your geologists about the level of uncertainty and the problems that the ground can present. And we should scale our investigations based on that information. So let's look at another example. This is, I love this picture. We've got a geologist for scale here on the left-hand side. So if we put one borehole in, well, I might see an enormous cavity right here where my geologist is standing. I might see pretty good rock, and they can be right beside each other. And the way you deal with that, because we're never going to drill everything, we're never going to have the perfect number of holes, is you have to understand what the ground is likely to be presenting to you and design your site investigation around that. So again, it's this kind of sort of risk decision making where you're thinking about what could go wrong, What happens if it does go wrong, and what do we do about it? So this is just a little diagram. This is actually out of the best practices manual that the Corps and the Bureau of Reclamation put together. Evenly spaced boreholes that are vertical may not be what you need. So in this case, this is actually a rock cut. So we've got some relatively evenly spaced borings, and this tan stuff here is, okay, well, we have soil. We have soil. And the dashed line is the interpreted top of rock. Now, if you saw this with just the 3 borings, you would go, oh, okay, fine. And maybe you probably wouldn't even think about it. But if you would, now that I can show you the overlay of what's actually in the ground, you can see very easily in this case how 3 vertical borings can really mislead you about what's happening. And you can imagine there's definitely a different construction cost if we have to remove all of this rock and we think that that was soil. So a lot of times what we'll end up doing is rejiggering how we do things. Maybe we add more boreholes. And so look at the blue line versus that black dashed line for where the top of rock is. Also, when you've got vertical features, we do a lot of inclined holes. Okay, inclined holes can be a little more expensive. They're not appropriate for every situation, but we routinely do this underneath dams when we do grouting projects, precisely because vertical holes are really, really bad at capturing vertical features. They're easy to miss. So think about what the problems could be with how you're designing your investigation, and then roll in from there. So let your geotech and your geologist help you. Here's the site. Come back and tell me what you think you need. Let's have a discussion over the risk tolerance that we have for this project, the schedule that we have for this project, and let them pull some old information, because what you may find is there is a lot of old information that would be extremely helpful for how you're planning out your site investigation. This is actually from Kentucky Lock and Kentucky Dam. Massive vertical karst features beneath that. And we're actually in the middle of constructing a new lock at Kentucky Lock. And so we knew, because of the previous photo, this one, to expect features like this. And so that was incorporated into the design. And because you can anticipate this, you're going to reduce the impact of cost and schedule risk on your project. If you suddenly find a massive karst feature like this underneath your lock construction, and then you have to negotiate how to deal with it in construction, of course it's going to cost more, right? That's going to make life more difficult for everybody. So we've got to design our investigations with this idea that we need to understand what's happening in the subsurface first, or likely to happen. So what are the kind of risks that we're talking about, right? Well, we're talking about risks that lead to certain consequences. I'm not worried necessarily about risks of, so-and-so didn't read my report. Project design failure, right? The design does not work. Okay, that's a big risk. We don't ever want to see that. Life loss or safety implications, right? Oh, well, that's definitely a problem. If our bridge falls down after we've built it, it looks bad on everybody. Property damage, and you definitely don't ever want to be in a situation where you have life loss from your project. Property damage that adds to the cost of the project. Project cost growth and schedule delay, right? How critical is that schedule for you? Maybe this is the first in a series of projects, and if this one misses it, it has this cascading effect on a whole bunch of other projects. And cost growth. I mean, everybody's always going to be concerned with how much something costs. When we make promises on projects about what the cost should be, our clients, whether you're working for a private AE firm or you're working for the government and it's the taxpayer, they're going to want to know why suddenly it costs so much more. And you have to be able to explain that. And then there's also public perception and reputational impact, right? If something goes badly wrong publicly on a project, that is a risk. And it can lead to problems for your organization. All right, so why do we face these kinds of consequences? There's been a lot of ink spilled over this over the years. This one's from 1981. 90% of dam failures in history have occurred because of oversights that could have and should have been avoided. All right, we don't ever want to be realizing risks that we should have known. Those really, really hurt. 80% of civil engineering failures were due to human, organizational, and knowledge uncertainties as opposed to engineering issues. So we've got to get after what we know and what we don't know. And we've got to understand what that band of uncertainty is. 60% of deep excavation failures in the Netherlands were caused by not applying existing knowledge. So if you approach a deep foundation and you say, I want one hole here for each drill shaft, but you don't go back and pull the information from that may already be there, you're already starting behind the 8 ball. You're already taking some of the knowledge out of the situation and not necessarily doing very well with it. 88% of excavation pit failures in the Netherlands could have been avoided with proper risk management prior to work. Wow, those are some big statements, and all of these are published in the literature. This is nothing new, and as you can see, from 1981 to 2009, and there are plenty of other examples in 2020 and 2021. All right, subsurface related impacts. 80 to 85% of European building failures are related to ground problems. 2004, and I don't think we've gotten that. We've gotten that a lot better. 50% of project delays caused by adverse ground conditions. Despite the absence of definitive statistics, most experts would agree that the incidence of geotechnical disasters has increased over the last 20 years. And that was written in 2011. Wow. Okay, now I know I'm talking to a bunch of structural engineers, and you probably are all going, yeah, you geotechs, man, you don't know anything. Well, we do. And there's a lot of issues that go into this. There are a lot of decisions that we can make in a project that bake risk in. And people don't always realize where they're baking that risk in. And that is one of the reasons why, as an engineering team, we've got to be communicating back to our clients, to our project managers, and to our stakeholders what the risks actually are versus what the cost and benefits of the project and what the costs are for construction. So a couple of examples of some geo-related risks, right? Soil and rock mechanical properties. This is a picture of one of the cutoff wall construction. If through a dam, if the rock is significantly harder to cut than we think, that is an expense. Depth to rock, unexpected subsurface materials, groundwater elevation and pressure changes, internal and surface erosion, and insufficient investigation to sufficiently mitigate the subsurface risk is really what gets us. All right, so this is from an NCHRP study. This is a bunch of highway departments. And it's not entirely, maybe it doesn't capture absolutely everything, but they came back to the highway department and highway agencies and said, hey, how much are you spending on subsurface change orders? And they're coming up with rather a lot of money. Qualitatively, it's a priority concern for most agencies. Many agencies were not able to actually quantify the exact amount. But you can see here from Indiana, it can be a fairly substantial part of their budget, and it represents up to 17% of all agency change. But we're spending only 0.2 to 0.5% of construction costs on the subsurface investigation. So you got to stop and think, hey, wait a minute. Maybe if I'm too small and slicing it down too far in the site investigation, maybe that has a cost that we are realizing later in the project. Now, at Corps of Engineers, we've been looking at some of this as well. Now, we definitely have some of these. And what we're seeing is that it varies across project types. On a really big project, we do a ton of investigation, and you see these claims be a lot smaller. But in terms of total cost for our program, roughly in the last 5 years, it's accounted for about $25 million each year. Well, that adds up after a while. That's money that if we could anticipate ahead of time can be spent on other projects. And certainly we've got a number of delay days. And again, this sounds like a lot, but this is not one project. This is the entire civil works portfolio. And roughly, it's coming out to, in some of our early numbers, at about 3%. Well, if we're going to pay 3% on the back end and only 0.5% on the front end, we have an opportunity here, right? We have an opportunity to make things better. Now, sometimes these things are unavoidable. There are residual risks, and we're going to talk about those in a minute. But there's definitely an opportunity here to save some money, to do a little bit better, to push things forward, and to have more funds available for other projects. Now, this is something that came out of the NCHRP study, and it's just a couple of USACE data points as well. So what you notice is we know there's got to be an upper bound. We know you can't just keep spending money on, the answer is not 40 million borings. The answer is the right borings at the right time in the right place, using the right tools. But we can definitely see that when we are not spending very much on our geotechnical investigation, we have a whole lot more spread and cost growth. So a lot of folks are actually looking at this kind of a chart, gathering even more information, because we want to try to define this a little bit better. We want to go after the right projects as well. Again, you may have some kinds of projects where you have very little problem, and you may have certain types of projects where we have a lot. And we want to be able to look at that and be able to define it. All right, so how much info do we need? Well, look, drilling more holes is not necessarily the answer. I love a drill rig. I love a drill rig. I started out my career behind a drill rig. And I've definitely been the person that everybody's rolling their eyes in the room saying, oh my gosh, she said she needed 5 more holes. But there is no one size fits all. You've got to come at this with a risk mindset. You've got to come at this with good engineering judgment. And you've got to think about what is the price that we are going to pay if it goes wrong. That's the kind of thing you need to be making sure that you're bringing in. Now with that, I'm going to actually pass it over to Georgette. And Georgette, I'm going to continue to run the slides if you don't mind.
Yeah, that'll work great. And I'll keep my video off just to make sure things run smoothly. So I'm going to get into the discussion of risk management. And I put the definition up here as a systematic process of identifying, analyzing, and responding to risk for the entire project life cycle. I put that in there because it's something that you're going to look at from planning through engineering designs and through construction, all the way into operation and maintenance, to make sure you understand what is going on in your project and what information is changing your understanding over time. So in order to do a risk management process, you would start out by first sitting down with a team. And of course, when it's a project that involves anything founded on land, you're going to need a geoprofessional. You need a geotech or a geologist, and typically both would be preferred, especially if you're drilling into the subsurface, to kind of help you identify risks. Okay, so you're going to identify your geotech risks, your hydraulics risk, your environmental risks, all of those in a portfolio fashion. So when it comes to the geotech risks, though, you're going to work with your geoprofessional to establish, okay, now that I've identified those different types of risks, and Vanessa showed a slide on, where's top of rock, and could I miss that, or might I have a dewatering issue? What is the likelihood that I'm going to, have that realized, and what are the consequences? And after I kind of looked at that, I'm going to rank those risks and prioritize what I'm going to address, establish a path forward, and then go ahead and manage the risks over time and update my understanding. So making it a living type assessment. Okay. So next slide, Vanessa.
Sorry, it's running slow. Okay.
So I'm going to walk through, once you've identified what the risks are on the project, and we're not going to go through that exercise, but because it would take some time with your team. But once you have, you'd walk through that. There it is. Okay. And you walk through each and every risk and systematically go through and identify, what is the probability that that risk is going to be realized? And go ahead and work with the team to, describe what the definition of very high, medium, low, and very low are, so that we all have a calibration of what we mean by probability. So I have some listed here for very high, greater than 80%, very low, less than 10%. This is for a specific project that we use, and this might be different for your project needs. The idea is to communicate with the team, what do we mean by a very high probability or a very low probability, and all be on the same page and establish that for the risk. Then you're going to go in and you're going to look at, now that I know what the likelihood is, I'm going to say, okay, what are the consequences of the risk being realized? If you could forward a slide. So I'm going to go through the same exercise for consequences of the risk being realized. I'm going to say, okay, what would happen? Would I have a cost growth? Would I have a schedule growth? Are there some safety implications? Is there some political or public perception implications? And I'm going to define what is very high, medium, low, and very low again for these consequences. And again, we're going to work on a team consensus to calibrate everybody's thinking so we're all talking about the same thing. This is, again, an example, and it would be adjusted for your project needs. But once you've sat and you identified, okay, what are my risks? What are the likelihood of occurrence? And where's the probability? I'm going to put that all together in a risk matrix. Again, this is for each risk. And I'm going to say, well, if I have a very high probability and a very high consequences, man, that resultant risk is really severe. I'm concerned about that. So I'm going to put that as a high priority to address that in some way. If it's maybe a medium probability with a very low impact, okay, you know what, that's considered a little more minor. So I might not want to address that the same way I would address something that had a severe resultant risk. And of course, if you had something with very low probability and very low consequences, that could be negligible, and you can maybe even look past that one and really focus your priority addressing those severe and substantial risks. Let me go to the next slide. Okay, and something the Corps does is once we have all of our risks identified, we develop a risk register. And again, this is not just for geotech. This is including, you know, planning and H&H and cost and environmental. And we list all these out, and we get an understanding of, okay, what is my risk rating on this project as a whole? How many high priority risk items do I have? How many moderate and how many low? And really assess, you know, where do I need to focus my attention? And I want to really document this and be able to update this over time. And that's key, because it's a planning process. You might say, you know what, I think I have a really high risk of not really being able to build this project here, because I think the top of rock is really not low, but I don't know for sure. But as time progresses and you obtain more information, do some subsurface investigations, you're going to have an increase in your confidence and your understanding of what's going on, and you're going to readjust what you think that risk is. And it's either going to go lower or it's going to go higher, and it's going to make you change your decision on course of action. And that's where I'm going to get to next, is this established path forward. And this is on the next slide here. So the four main things that you could do to kind of address the risk. The first one is mitigate the risk, okay? What can you do to mitigate the risk? Well, you can do additional subsurface investigation. You can better understand what's going on. But of course, that's going to come with time and money. You could transfer the risk. You could say, hey, you know what? I'm going to put the risk on the contractor and say they're going to deal with it. But of course, that's going to come with a pay increase on the actual contract cost. You could say, you know what, I'm going to avoid the risk. I'm going to change the project plan and try to eliminate that risk and protect the project from these impacts. That could come at a cost as well. And it can also come with upsetting some folks who wanted the project to look a certain way or be in a certain place. The other option is to accept the risk. You could say, hey, you know what, I'm okay with this risk. I think it's fine. I have built in some contingency. I'm going to go for it. And if it happens, I will plan for it, and it'll be okay. And that's done in a lot of projects. Next slide, please. And I think we discussed this a little bit, but of course it's, you know, making sure we don't just do this once and walk away and say, hey, at the beginning of the project, I've identified my risks. I think they're low. I think they're fine. We'll keep going. It may happen as you progress through the project and you get more information, you realize, you know what, I think my risk is a little higher than what we originally estimated. I think we need to address this, and we need to change our plan over time to make sure that we are mitigating appropriately or walking into it with eyes wide open, that we know what we're getting into. And of course, we have to communicate the changing of the risk over time. And Vanessa touched upon that at the beginning. It's like, as you go from the planning into engineering design, there's always a question, well, you got some subsurface investigation. That should be enough. Why do you want more? It's like, well, our understanding is changing. We see something here that we didn't see before. And so communicating that is critical. And I'll show you some examples of using some visualization to help with that communication in a minute. But that new information definitely can be a game changer. So what about uncertainty? We've talked about that a few times during the course of this presentation, but it really does play a major role in decisions. A lot of times your risk might be coming out higher only because you're not sure. That I think I have a high risk here, but I just don't know unless I have an investigation to better define the subsurface, and so I can make a better engineering judgment. And that engineering geoprofessional really needs to be there to help communicate what they think the risks are and how they can be mitigated or avoided, or whether they think based on their engineering judgment that, you know what, we can accept this risk. I know this area, we have enough information, let's go forth and conquer. Next slide. Okay, so remember this, Vanessa talked about this previously. You know, that desktop study and walkover, ideally you'd have all this information up front going into design, gather a little more information and go into construction. But what we're seeing a lot is that typical geotechnical data acquisition, folks are saying, hey, I just want to put a little money up front just to get just enough information to get me going into the next phase. And sure enough, when you do that, you do end up in construction, and then you end up with those cost increases. Like, well, why didn't we know that? So we need to make sure we're smart about our investigations and which tools we're using to make sure that we do have a good understanding of what's going on. Next slide. So I put this in because a lot of folks, when you're talking to them about subsurface investigation, the first thing that comes to mind is borings. And we saw that at the beginning of this presentation when we asked, okay, what do you think of with subsurface? And everyone said we had a big borings up there. And that's true, because that's where everybody's mind goes. It says, okay, I need a huge drill rig. I need to go out there. It's going to be slow going. You're going to have a geologist. They're going to be logging every single hole. It's going to take forever. But we can fill in a lot of the data gaps with a lot of different tools that are out there. And this is an example of a karst investigation, trying to determine where the top of rock was, where we have karstic features, and what does the groundwater flow look like. And so in this case, they use geophysical methods to kind of fill in the gaps between the boreholes. And where something looked a little suspicious or concerning, or we want to know a little more about it, we could target those specific locations with borings, rather than spacing every 100 feet, let's say, or saying, oh, for every square footage, let's do this number of borings. Here you can really say, I'm going to target where I'm going to go. There's other tools you can use, like destructive drilling, and using cameras to speed up the process and really see what is in the subsurface with camera imagery. So there's a lot of tools out there, but you need to consult the geoprofessional and say, hey, can we use some CPTs here instead of borings and maybe gather information that way? Would that speed up the process? Is that sufficient for this project? And your geoprofessional will tell you, yeah, we can fill in some of those data gaps and provide you more information and identify other areas that are specific that we might want to target a little closer. Okay, next slide. Okay. So we talked a lot about uncertainty and confidence, increasing your confidence, but there is a potential for overcompetence on projects. And we get that a lot, where they say, you know what, I think the risk is not that bad. We're just going to go ahead and go with it. And I like this chart up here because it kind of shows you your novice engineer versus, going from left to right on versus your expert, and actual knowledge. You have a little bit of knowledge at first and it grows over time. But then if you see the red line is your self-estimated knowledge. So, when you're first going into your career, you kind of overestimate what you think you know. And then over time, as you gain more experience, you realize, man, there's a lot you don't know. And you learn on jobs by making those mistakes, by taking those risks that maybe you shouldn't have. And over time, you tend to underestimate that self-knowledge because the real world kind of hits you. It didn't hit this board of consultants, though. So in 1958, there was a board of consultants brought together for a dam project, and they reviewed the geology and the information they had at hand, and they recognized that there were some leakage risks resulting from unknown and indeterminate ground conditions. But they believed that the known conditions are sufficiently favorable to justify taking the risk. So of course, here they said, we're going to accept the risks, we're good to go. 80 years later and $3.6 million over budget, the project, in this case the dam, did not meet its intended purposes due to complex geological conditions encountered. So could a little more investigation up front and identify those unknowns and indeterminate conditions save a lot of money? I would argue yes. Okay, next slide. All right, caution also applies to technology, and you folks probably see this as well with a lot of the analysis you do. We're increasingly relying on our computer software and technology, and those are getting increasingly complex. And so, especially when it relates to geotech, we want to make sure that the geoprofessional and an experienced one is involved to make sure that not only are we using the tools and applying them appropriately, we need to look at those input parameters. Do we have enough subsurface information to really put a good estimate on what the different subsurface parameters are? Are we relying on one boring for a 3,000-mile stretch of levee? If that's the case, then this is garbage in, garbage out. We really need more information to really understand what a good set of parameters are. We also need ground truthing. You cannot engineer from a desk. You need to get out into the field and do a site visit and understand, what does that topography look like? What does the exposed geology look like? What do we know about the area? And when we see our data coming in telling us something, does that make sense? So here on the right is INSAR data, looking at settlement of an area of the topography, and those hotter colors are where we see more settlement, and blue is either less settlement or a little bit of heave. And you see a little red circle there. That red circle correlates to I have two guys standing looking at a sinkhole. So the data completely missed this because of vegetation overgrowth. So you can't, rely solely on digital data coming in. You have to compare various data sources and get out in the field and make sure what you're seeing makes sense and that there's not something else going on. So next slide. Okay, data management, visualization, communication are critical, and that's true for every discipline in engineering. You can grab your data that you have that's historic, maybe it's in some files, you have some digital data, you have some models, pulling them all together and using them to explain what's going on is the best way to communicate the needs of the project and to understand if your project is actually performing as you want in the end. So not just in planning, all the way through design and post-implementation. Next slide. I'm going to give you an example of this in a second. Sorry, there's a little bit of delay. Okay, so here's an example, an overview of a dam project, and it was, going into design. Those yellow triangles with exclamation points are areas where there were some potential concerns with a project. So the idea is to better understand what are these potential concerns that happen to be related to seepage and piping in the foundation, and what is the design that we need to address them. So of course you're going to need to have some sort of a desktop level study to understand, well, what do we know about this project? So you see an overlay here of an old drawing that was pulled out that shows grout holes that were done as part of original construction. So what we did is we took those grout holes and digitized that information and said, okay, well, where are all these places in space geospatially located? You can go a little faster on this. Thanks, Vanessa. And you can see a concentration of holes, just quantity in certain areas in the center of the dam and then also on the right abutment. Now, if you took the grout take information, how much grout was pumped into these holes, you can see hot colors showing higher areas of concentration. Overlaying what we know about the geology, you can say, okay, some of this may be related to geologic features that I have going on. Now I can plan and target my subsurface investigation to better understand what's going on and put those boreholes in locations that make sense. I can overlay where I have existing information, identify those gaps, and plan accordingly. Next slide. I'm going to show you another project here. This one is Pine Creek Dam. Okay, this is just an aerial view. It looks a little bit 3D, pulled in GIS. But if I strip away that surface, I can expose where I have information showing where top of rock is. I can also see my intake tower connecting to a bridge and the bridge connecting to the center line of the dam. And I have a conduit going from upstream to downstream. I can overlay my subsurface investigation results and really clearly articulate to someone that, hey, I put up a bunch of subsurface investigations along this conduit, and I have some standard penetration test results that show some concern along this conduit, and that could lead to seepage and piping. So looking at where those are and then looking at additional information about the impervious core and the vertical sand filter at the dam, I could say, you know what, this led ultimately to a modification of the project, but it was really easy to communicate the need visually by pulling this data together. Ultimately, we had a new barrier wall, a concrete sinking pile wall placed in along with new sand filters. But the other thing we can do is not only plan and explain why we need to do what we need to do, but during construction, we can actually monitor the project over time and look at these concrete panels and say, what are the different test results I have? And let me spatially locate them. And then let me look at the test results and say, hey, are there some areas of concern? Where are they? Are they in critical areas? Are they at the ends of the wall that are maybe a little less critical? Are they near the conduit where I might be more concerned? And then I can take these in different views, of course, and say, all right, I want to understand where did I think top of rock was? Where was top of rock? How far into top of rock did I get my my panels? And did I meet those overlaps? And what were the test results for that concrete? Was my concrete slump meeting specification? And if not, can I highlight that and see it spatially? Do I care? Do I care that the leftmost side of this has a 4.5-inch slump instead of greater than 5? I could also say, you know what? I want to do some verification drilling, and I want to verify that the concrete quality meets what I spec'd out, and I have no concerns. And so what we do typically is we put some cores through these concrete sink-in piles, and we pull out the cores, and sometimes we put in optical televiewers. And we use the optical televiewer to create a borehole image of what is in situ inside that wall. So we'll go through and we'll identify areas that may be suspect or may have a potential defect. And if we locate these spatially, we can click and say, all right, well, this one may be of a concern because it is kind of near the bottom of my secant pile. It's near where my conduit is, my area of concern. But I pull up my image and I can see, okay, I can make an informed assessment of, hey, is it a risk to keep this there? Do I need to do more in my design? Do I need to reinstall a pile here? Or can I accept this given its location? All right, next slide. So we didn't talk about this much. We keep talking about top of rock and joint features, and but we often have problems with groundwater. You know, what are those piezometric pressures? And just like with the other examples I showed you, you know, using digital information and managing the information and visualizing it it's a picture worth 1,000 words. Here we've color-coded piezometric contours with, you know, warmer colors like yellows and reds for higher pressure and cooler colors for lower pressures. So this is a way you can kind of see, you know, as you're, you know, planning for the project, where do I have those higher pressures? And as I'm implementing the project, how are those pressures changing? And then at the end of the project, you know, what did I change over time? Did it meet my design intent? So you're preparing for construction and then post-implementation evaluating, you know, what did that project change at the site? So I'm not going to go into detail on this, but it was to help communicate visualization of information and, you know, being able to explain to someone what you're seeing and what's going on. And always remember, okay, so we've gone through a lot of discussion so far, but we can reduce and mitigate risk. We can do a lot of subsurface investigation. We can do geophysical exploration. But we can never eliminate the risk, all right? And it's said best by this quote here, Randall, residual risks are unavoidable because ground is the greatest uncertainty in civil engineering. And you can see that this example, and on the right, it looks like a cartoon, but it's pretty realistic of one of our projects. You can see, you know, boreholes completely missing one very large karst feature, and only one of those 5 holes actually hitting a very small, relatively small feature that was fairly deep in rock. So, you know, you can do a lot of investigation, but you're never really going to eliminate that risk. But we can do the best we can to plan accordingly, make risk-informed decisions, and target our exploratory programs to reduce uncertainty and better understand the risks that we're getting into. All right, next slide. Okay, I have a quick case study I'm going to go through, and it's a tale of 2 water control projects. And this clearly, you know, shows what we've seen a lot on a lot of projects. You got a southern structure, and you have 2 northern structures. Okay, and this is why good site investigation and geotech engineering matters. Next slide. So our southern structure had some site-specific characterization performed. Multiple borings and traditional geotechnical analysis were performed to understand, you know, what's going on. The geotechs and the structural engineers sat down together, they coordinated, they employed shallow foundation footings at the site, and they highlighted that there was some water mitigation that was needed, and so they addressed that by installing mill sumps and water collection trenches. So this project went really smoothly. There was no cost growth, no time delay, risk was mitigated with subsurface investigations. That's awesome. Next slide. So what happened here is what happens on a lot of projects. Something came up where there were some additional features that wanted to be constructed, very similar, they're water control structures, but these were on the northern end of the project. So the geotech said, you know what, we only have 1 boring in this vicinity, and based on what we know in the area, this is highly variable geology, and we're concerned that we don't have a good understanding of this area. We need to do more subsurface investigation. And not only that, we want to perform some additional analysis to make sure that we are designing appropriately in this area. And of course, project management came back and said, no, that's going to be time delay and cost. We don't have the time for you to do more analysis. You have enough information. We've done this before. We're going to go ahead and accept the risk and go forth with the project. You guys have never seen this happen, right? Okay, next slide. So we're going to repeat the southern structure design. It worked there, this is not too far away, it'll work here. Well, during construction, the boil started to form, and it was very quickly realized that the dewatering was very much insufficient. Deep wells and higher capacity pumps were required to control the water in the area. And then they found that the subsurface materials were of far lower strength than in the other structure location. So the foundation design ended up being completely inappropriate. And during construction, a complete redesign was required, and a timber pile foundation was ultimately employed. So the cost growth here is 55%. The time delay wasn't so bad. The cost growth was kind of a killer. Had they stopped and said, hey, you know what, let's take those 69 days and perform a few extra subsurface investigations and do that analysis, that cost growth would have been far less. Okay, next. Okay, so I'm going to take this to the key takeaways here. Early understanding of the subsurface helps avoid delays and mitigate cost increases. That really can't be disputed. Risk-informed decision-making is critical. You know, really understanding your project, what you know about your project, where your uncertainties are, and planning an investigation to help target where you need to add additional information. It's critical. You got to work with that geoprofessional, though, to make sure that you have a good understanding walking throughout the project life cycle, planning through engineering design and interconstruction and after, to really say, you know what, we did the best we could. You know, we saw what the risks were, we identified them, and we took appropriate action. And then, of course, data management, visualization, and communication, those are critical. Being able to show folks that, hey, here's what we know, and let me show it to you with a picture. It goes a long, long way. Especially when you show someone a map of your project and your project footprint and the location of one measly little hole, that will help communicate that the need for additional subsurface investigation. And of course, structural engineers and geoprofessionals, when we work together, that usually brings out the best success. Okay, that was a lot, but I think we're at about time, and if you're okay, we're okay with questions.
Yeah, that sounds good. Ask anybody. You can type your question into the chat box, or you can come off mute and ask it directly. We'll give that a minute or two here. I think some of the risks that I've seen, Georgette, are the same thing you're saying, that professional judgment and experience comes from people who know what they're talking about, and a lot of times risk comes up when we try to cross disciplines and things we're not trained in. Okay, so I'm not seeing any questions come through. That means you guys hit it all, and you get an A+. I appreciate all of your efforts today. I did pull my slideshow back up. Can you guys see that here?
Yeah, we got you.
Yeah, thank you. Vanessa, thank you for pointing that out. Yeah, if there's any other questions that come through later on, feel free to email, or we'll follow up as needed. So just want to take a minute here to say thank you to Georgette and Vanessa. This has been really informative, and I think if we can enact it, it's going to be good for our projects, geotech and structures, moving forward. A little preview, we have a thank you gift we'll send you. It looks an awful lot like that pint glass in the picture there. So we'll be sending that to offer a small token of our appreciation. To everyone else, to our members, our next meeting is going to be at 12 o'clock, lunchtime on October 28th, and it's going to focus on building information modeling, BIM for bridges. So hope to see you all there. Look for a registration link to come out. And then we did have a few things from our SEI national leads they asked us to share, so we'll just spend, I'm going to go through this very quickly. Member benefits and resources. If you're not a member of ASE or SEI as a society, we encourage membership. There's a lot of benefits that come out of that, professional growth, and also advancement of our industry. we can share these more. I want to respect everybody's time. Opportunities to get involved in conferences and volunteering in publications. If you're not near Philadelphia, where we're slated, there are chapters across the country here. With that, I am very thankful for everybody who took the time today. Thank you to our speakers, and we look forward to seeing everyone at the next meeting. Have a good day.